So while we're waiting, I'll just mention, so we're looking at two Ryugu particles that we got allocated by JAXA. We performed a number of analyses on these over the last year or so, focusing on synchrotron and laboratory X-ray techniques, and as well as vibrational spectroscopy. So these are the two particles we got, A0030 and C0034. So chamber A was those particles were collected from the surface of the asteroid Ryugu. Chamber C, those samples were collected from the subsurface of Ryugu or samples that were mostly in the subsurface after an artificial impact into the asteroid. Each of them is about a millimeter across or so. They were allocated initially to my collaborator, Mehmet Yeseltas, and our team, led by Yoko Kebukawa, was able to take small portions of those, embed them in sulfur, which you can see on the left here, and then we had flat microtome surfaces that we could do some analyses on. So here I have a movie. If you could play that in the back. This is a XCT movie. So we're doing X-ray. Oh, come on. You can keep going. We did X-ray tomography on the sample where, can you try hitting play again? Sorry. It's just not going. It's not happy. Oh, well. This is really cool. You can find me later. I'll show it to you. But we're able to see the interior of the sample. You can kind of think of this as almost like an electron backscatter image as we're going into the sample, where the bright things are high Z elements. And so the really bright particles are mostly iron oxides and iron sulfides. We can, as we're going through the particle, we can also see how the pore space and the cracks are changing. So we're working to actually quantitatively calculate what the porosity of these samples are, as well as the abundances of different phases that we can infer based on their Z number in these. So I'll keep going. This is not, can you advance the slide? Sorry, because it's stuck, I think.
Yeah, might have to restart.
There you go.
Okay, thank you.
Oh boy, okay, I went way far. Okay, let's try again. All right, so the bulk of this analyses we did though were on whole particles in some of those small sections. Right down the road from us at Stony Brook, we have Brookhaven National Laboratory, which has the National Synchrotron Light Source 2, which is one of the brightest synchrotron X-ray sources in the world. And so we actually did work at two beam lines, the TESS tender energy spectroscopy beam line and the X-ray fluorescence microprobe, where we did micro X-ray fluorescence mapping of elements. And you can see the elements down there on the right, as well as some micro XRD and some XANES, which gives us element speciation. So what you're looking at here are the whole particles from A0030 and C0034. And the color coding is element specific. So both particles, as we would expect, given that these are mostly made of phyllosilicates, are dominated by silicon. But we also see with the TESS beamline, we're sensitive mostly to light elements. And so the brightest red pixels are phosphates. And so we have actually a decent amount of phosphorus in these samples. And the brightest, the hottest kind of greenish pixels are metal sulfides. When we look at the two samples, they actually appear quite different, with A0030 being more heterogeneous with larger compositional variations compared to C0034. We can also do element speciation mapping. And so we can actually tune the energy of the X-ray beam such that we can tell the difference between sulfate and sulfide, for instance. So sulfide and sulfate in this section of C0034 both occur within discrete locations. In this case, sulfide is green and sulfate is blue. And there are some places we can see those purple pixels where sulfate and phosphorus co-occur together. So sulfate and the phosphate co-occur. The sulfide accounts for about 90% of the sulfur in the sample. Sorry, sulfide occurs for 90% of the sulfur, with the rest being mostly sulfate, we think. Now, this is interesting. So kind of the initial analysis of the Ryugu samples, everybody suggested that the sulfate is all due to terrestrial exposure. We think there's probably some evidence for maybe some endogenous sulfate in these samples. For instance, we don't see obvious reaction rims around the large sulfide particles. The sulfate and the sulfide don't co-occur relatively easily. It's almost certain that some of the sulfate is due to terrestrial atmospheric exposure, but we think some of it might actually be endogenous to the sample as well. The sulfur zanes really gives us the sense of what the speciation is. And so these squiggly lines here, I'm used to presenting infrared spectra. These are X-ray spectra, but these just like I'm used to presenting IR spectra, the shapes are diagnostic and the features are diagnostic of specific species. So in this case on the left, you're looking at several spots for zanes and XAPS measurements that we did for sulfur along with a pyrrhotite standard. And basically every spot that we measured with the synchrotron beam, which is about 5 microns across, was pyrrhotite. We didn't see evidence for any other sulfide species. And this is very different from, say, CI chondrites or CMs, where we see a large range of different types of metal sulfides. On the right, where you see the arrow, that's that peak at about 2481 EV. That's our evidence for sulfate, and there's more sulfate present in C0034 than in A0030. Now, that's kind of washed out, but one thing I'll just show here, this is just an SEM EDS map. I mentioned that our synchrotron beam size is about 5 microns. Just doing the SEM EDS, we can make maps of different metals. And what you're seeing here, these really tiny little purple pixels, those are iron nickel sulfides. And so I think our synchrotron measurements were just limited by the synchrotron spot size. When we actually do the higher resolution measurements, we see a population of sulfides that are much smaller that are iron nickel sulfides, whereas all the larger ones, which are in red here, are just basically pure iron sulfides. We also did phosphorus zanes. Most of the phosphorus in both samples is apatite, but we do see on the right some non-apatite phosphate in both of these samples, but it's more prevalent in C0034. The spectral shape is actually pretty diagnostic, and it precludes things like aluminum, calcium, magnesium, Fe3+ or manganese 3+ phosphates. But it could be iron 2+ or manganese 2+ phosphates, or maybe even an organic phosphate, which would be really interesting from a kind of prebiotic chemistry standpoint. So we're still trying to nail that down. We also did a bunch of vibrational spectroscopy on these samples. So this is Raman work that we did primarily focused on the organics in the sample. And so the two major peaks you're seeing in the Raman spectra on the left are the carbon D and G bands, and those change shape and position as a function of exposure to different temperatures. And so we can actually use this as essentially a sample thermometer, right? And so this is kind of a spectral thermometer where we can plot the peak positions and intensities like you see on the right. Those parameters plot very close to those of primitive meteorites like we would expect. And then we can apply some models to those parameters. And there's several different models that are out there that make use of these carbon D and G bands. But the key takeaway is that we have a very low estimated peak metamorphic temperature for the carbon. So less than 80 degrees Celsius. That's consistent with little to no thermal metamorphism of these samples. And then finally, or almost finally, we did micro and nano infrared spectroscopy. The Raman turns out to be very insensitive to the phyllosilicates, which actually make up the bulk of the matrix of the sample. But the FTIR is perfect for this. So we did both micro and nanoscale near field infrared, where we can actually get spot sizes down to about 20 nanometers per pixel and get really nice infrared spectra from those. So the nano IR spectra of the microtome section display mineral and organic heterogeneity at these sub 100 nanometer scales. These samples are actually very challenging to work with. My graduate student, Olive Corin, who's in the audience, spent a lot of time on these samples, which were very difficult. Yep. But we do see both saponite and serpentine. We see spectral features of both of those, as well as variable amounts of carbonate, water, and different organic CC and carbon oxygen bonds. So I'll just kind of conclude with like the big takeaways. These types of multimodal investigations of Ryugu particles take advantage of the really complementary strengths of X-ray and vibrational spectroscopy. By the way, if you care about the moon, everything I'm talking about here, we're going to be able to do with Artemis samples, too, and as well as Apollo samples that we have. So there's differing sulfate abundances in the two samples, but this is definitely not due to synchrotron beam oxidation. Some of it's probably due to exposure, but not all of it. We see interesting sulfur and phosphorus mineralogy, and then these Raman measurements indicate a very low peak metamorphic temperatures for the samples. Thank you.
All right, thank you very much.